to 42 cores.
Yeah.
So now the question is, can you feed all 42 cores, fast enough that the processors don't have to twiddle their thumbs, right?
Yeah.
So unless the processors, each one has a different memory bus to its own memory, eventually they still have to access the same memory and on the same memory bus. So if you don't solve that problem, you can have all the processing power you can have, but if you cannot feed the processors fast enough, then you're not going to be able to realize the potentials of the entire system as a whole. Is that making any sense?
Yeah.
Yep. And that has always been, the issue. Caching helps a lot, because caching means, each core can store its, most recently or most frequently used, instructions and data, so it doesn't have to go out to the memory bus to get something else. Okay, so it helps a lot, but that depends on, how people write their algorithms. Certain algorithms do not lend itself to locality. How many people have taken data structure? Some of you. And do you still remember binary search?
Oh yeah.
Okay. Now, well, some people may remember binary search from my class too in P300. Okay. Now, binary search has a very strange, access pattern. It doesn't access an array sequentially. Okay. If you access an array sequentially, DDR2, DDR3, DDR5 technology will help, because when it fetches, the next, 20, 32, integers, it helps because you're going to need that, eventually. But in binary search, it doesn't help at all, because how does binary search do? How does it do the search itself?
Just like an ALU. You go either left or right.
You go either left or right, but you start from the middle, right? And then you go to the middle of either side, then you go to the middle of the remaining portion, and so on. So when your array is really huge, one access from the next access, they're not adjacent at all. They're not even close. So that means DDR technology is not going to help, because fetching the next 32 elements from the same array is not going to help you. So certain algorithms, like binary search, and I think quick sort, probably does not benefit from DDR either. So a lot of those algorithms, do not benefit because they access memory in a more of a random, or it spaces out. So the caching and also the burst access technology doesn't help that much. The other thing that we also are seeing is the size of the opcode. In other words, when you look at the actual binary code of instructions, they're also getting wider. If all operations connect to memory to the ALU, then each instruction must be able to specify one of the 4 billion locations in memory, assuming we have a 32-bit machine in memory for the first value, the same for the second value, and one to specify where to store the value. In other words, think about this in C terminology. The instruction is like a subroutine, okay? So when you look at the prototype of this subroutine, it has at least 3 parameters. Okay, 1 parameter to get the first operand, to get the first parameter, 1 to get the second one. So the first 2 are the input into the ALU, and then you need a third one to specify where to store the value. Each one, can be one of 32. Each one can be one of 4 billion locations. So you need 32-bit. For this guy, you need 32-bit for this guy, you need 32-bit for this one. So just to specify the 3 operands, you're using 96 bits already. This is not even to count the opcode itself. We haven't even talked about how do you specify the instruction itself, add, subtract, compare, and so on and so forth. You're chewing up 64 bits just to specify where to get the first number, where to get the second number, where to store the number. Okay, making the instructions that wide, would that help? It doesn't help at all. Because when your instructions are really wide, it also means, in addition to spending time, with you to the library to get the numbers that I'm supposed to compute, you also have to go to the library to get me the next instruction to execute. And those instructions are big and wide, so it might take you 2 trips just to get me the next instruction. So I have lots of time to twiddle my thumb. Okay? Does everybody understand the issue with opcode size? When everything comes from memory. So that's basically what this slide is. So the question is, do we have a solution? Well, the solution is the use of registers. Registers solve both of the problems. Okay. First of all, registers, in terms of on the silicon, they are very close to the ALU. In other words, if this is the ALU, physically, you have registers sitting pretty much right next to it. Okay, so when you route signals from the registers into the ALU, it doesn't take that long. Okay, these paths are relatively short, where the registers can fully keep up with the speed of the ALU. If your ALU is capable of doing 2 billion calculations per second, the registers can feed and store values at the same speed, unlike memory. Okay, so that's the first thing. It's kind of like with a TI calculator. I'm now upgrading my TI calculator to have the ability to store certain numbers. Not a whole lot, but nonetheless, it is on the calculator itself now that I can store numbers. So it's physically close. You don't have to go to the library to store or fetch the next number. It is fast. It can keep up with the calculator. Now note that registers are not a part of memory. It is not considered memory at all. Registers are completely a different concept. The other thing you also have to know is there are only a few registers. It depends on the architecture, and also depends on, in the case of the 386, depends on how you look at the processor, which mode you run it in. I would say it's between 8 to 16 registers. Okay, instead of billions of locations in memory, you now only have at the most, teens, in the teens, tens of registers. How many bits do you need to specify one of 16 registers? Come on, you guys can do it.
Two bytes.
Okay,
16 bits.
Okay, let me rephrase that question. If you're designing the opcode, and a part of the opcode has to say which register am I going to use to feed this part of the ALU, and you have 16 registers to pick from, how many bits do I need to specify which one of the 16 registers I'm going to use? How many bits, not bytes?
5.
2 to the power of what is 16? 4, okay? 2 to the power of 4 is 16. So therefore, only 4 bits is needed to specify each operand, compared to 32 for a 32-bit architecture. Now that we have 64-bit architecture, there's no comparison, right? So in a design like this, where everything is independent, we have 4, 4, and 4. We only need 12 bits instead of 96 bits to specify the operands, which is a big improvement. Now the number of registers is limited. Partially it is because of the physical limitation of the interconnections necessary to connect registers to the ALU. So that's part of the equation, and part of that, at least for the Intel processors, is just legacy. It really is just we have so much legacy software written in the old opcode. If you suddenly make the new versions of processors have 64 registers as opposed to 16, most of the software cannot make use of the other registers. Okay. How long do you think it takes for software vendors to start to utilize hardware features in processors? The next day, Intel says, well, you know what? We got this really cool new feature. Microsoft, get it and go like, oh, because of the time zone issue, we have a half a day delay. Now that feature is in Windows. No, it doesn't work that way. About half a year.
No.
Half a decade.
Yeah.
Okay, half a decade is the norm. Okay. Well, to understand that, let me ask you this question. See if you guys know your computer history well enough to answer it. When was the i386 processor released? We're talking about the 386.
86. 86, 87.
I would say 86, 87. That's about the right time frame. And when do you think a consumer? Okay, what is the first consumer-oriented operating system from Microsoft that makes use of the NT kernel? We were just
Windows
talking about
NT.
this morning in
Windows NT.
Windows. Well, Windows NT was not for consumers. That's mostly for servers and also business applications.
Windows XP then.
Windows XP, that is correct. And Windows XP was released when?
2002.
2002. So we are counting from 86 to 2002. 16. That's how long it took for a technology that was in the processor. Okay, virtual memory, different levels of protection and stuff like that. They were all there in the i386 processor back in 1986. But as far as consumers are concerned, the first operating system to truly utilize virtual memory and stuff like that was Windows XP. Windows Millennium, Windows ME, is exactly how many people had it and liked it?
Had it, so liked it.
How many people had it installed at least for a year?
I used it.
Exactly, and that's because Windows ME was based on was the last version of Windows that was still based on DOS, and because it was based on DOS, it had some of the memory protection feature utilized, but not full virtual memory, not full protection from so the kernel runs in a separate space and applications cannot crash the kernel. Okay, so it took 2002 minus 1986. It took 16 years. Somebody said, yeah. It took 16 years, not half a decade, for a hardware feature to be utilized in a consumer oriented product. So now you can just imagine if Intel says, you know what? Now you have 16 registers instead of 8. Great. How long would it take for software to truly utilize the extra registers?
Longs.
Yeah, exactly. Now, okay, when you say long, it depends on which operating system you're talking about. Okay, when you're talking about Microsoft operating systems, yes. But what if you're talking about Linux or FreeBSD or one of those open source operating systems?
Because people around the world can work on them, they tend to update faster because people who are interested in using the new technology will
Now,
update.
it is not uncommon that Linux will be ported to an architecture before the silicon is even ready. Okay. Now, when people design processors, for those of you who want to specialize in computer engineering, you will do all kinds of projects like this. When you go through the program, when people design processors, they don't test the processor, after it is on silicon. That would be kind of stupid because it costs a lot of money to put a processor on silicon. Okay. So what they do is they run simulation first. Okay, they would design the processor, they would finish all the specification, these are the opcodes, these are the registers, this is how everything works. Everything is going to be specified and to the point where it can be simulated. And in simulation, it will run really, really slow, but for the most part, it will behave the same way as if it is on silicon. Linux has been